Welcome, everyone, to Mark Voids a Warranty, usually with a hammer. I'm Mark, and I'm here to see what's inside this network hard drive. It stopped working, I don't know, about 3 years ago when I unplugged it, and it hasn't communicated since. So anyways, we're going to see if we can't get inside here and get the hard drive out. There might be some data on here, so I don't want to take this hard drive apart, but I did find one that we can sacrifice in its place. So with that, thank you for joining me. I'll bring up the chat screen, and if you have any questions as we go, please feel free to ask them. Thank you for joining me today. All right, so this is the Western Digital something. It's a Western Digital hard drive. Basically just a little hard drive in a box, and as you hook it up to your network, you can set it to auto backup your stuff and whatnot. I've since moved over to a network RAID storage, so these little individual ones end up being a little more trouble than they're worth. But I don't really know how to get into it yet, so that's the first thing we're going to have to figure out. Does the back pry off? Is there a removable cover? I don't know. I tend to not research before I go on air, so you can watch me work the problem. If I did something like go to iFixit, I could figure out how to get into this in about 15 seconds. Because they've gone to the trouble of, oftentimes x-raying these things. Sometimes, let me go ahead and get over to a down view so you can see me pray on this as we go. But sometimes they'll x-ray. I imagine every now and again they just screw up, but they do a really good job. Anyhow, I am looking for any sign of a screw or a clip or anything before I start beating on this. You'll see screws hidden underneath stickers so that people know if somebody's gotten into it, because the sticker will be physically damaged. I don't really see any evidence of that here. Usually you'll feel the screwdriver poke through, or you even be able to see an indentation of some sort, and I just don't see any evidence of that. So something looks different about these plastic spots where those feet were, but I don't know. This could be, is that a sticker? What is that? Maybe not. Again, I could go to iFixit, but what's the fun in that? You guys like watching me suffer, don't you? I don't blame you. I'd like watching me suffer too. Let's see if it'll shift it all for me. Doesn't feel like it. Feels like it's connected firmly. I don't know, peeps. With each passing minute, my drilling hammer looks more and more attractive. No, I won't. I won't. Yet. All right. There's a little bit of movement. All right, so it looks like we've got some clips in. Oh. There we go. That just pried right open. Like it was meant to. Let's see. We're making some progress. Come on now. There we go. All right. Already, actually, a great deal more circuitry than I was necessarily anticipating. We've got the hard drive, and it's completely enclosed. I've actually never seen anybody do that to a hard drive before. I wonder if that was for thermal reasons or for something else. I am not entirely sure. Interesting. Fortunately, though, they didn't solder these things shut, so we'll be able to get it apart and look in there. All right. So the first thing I notice is we've got some unpopulated headers. So some parts where they didn't actually finish soldering anything on. I'm not really sure exactly what those are for. There's some writing there, but I think that's just a J4. That's not too indicative. FT1, I don't know. With the number of pins, it kind of makes me think it might be a UART connection. But the only way you'd really know is to sit there and probe it. And that's a little level of dedication to curiosity that I just don't possess for this device. Okay, well, let's keep going. Figure out why we've got that covered in the first place. I've seen a lot of hard drives and a lot of things. I've never seen one shielded like that. So the question is, why? And I can't wait to find out. Whoops. I mean, this is the thinnest gauge metal. I don't know what this is, like 32 or something. It is, you know, a step above aluminum foil. All right, so hiding inside, we've got a 2 terabyte hard drive. That's nothing to slouch at, even these days. Let's see. Looks like there's a couple more screws. There we go. So here's our board. Here's our hard drive with perhaps some data on it. It was a backup. Again, I haven't used it in a couple of years, but I'm going to take a look at it before I decide to send it off to the great hard drive repository in the sky. All right. Let's see if we can't get inside there and see what there is to see. I've been having internet connectivity issues today, so I didn't do a great job on advertising the stream on purpose, just in case I'm not even online right now and don't know it. I am recording it, but I didn't want to get people all excited and then disappear. Oh, there is some solder there, after all, isn't there? Okay. So we're partially soldered. I missed that. Might have to grab some cutters here in a minute. There we go. That works too. Come on. All right. So there is a control board. It's actually a lot bigger than I anticipated. Looks like they still did double-sided assembly, but that's interesting. I would have imagined this to be a little smaller overall. What I can see so far, we've got power in RJ45. RJ45 goes over to the magnetics, so this is not an integrated mag jack. Pretty sure that's the pulse transformer. And then you've got everything from Applied Micro That's the big guy. That looks like the main driver. We've got some things that are possibly memory. It's hard to say. They're all bottom terminated components. We'll put them under the microscope here and see what it is. So all of this stuff does everything from running the interface to the operating system. It does have its own operating system and web server built in. Over on this side, we've got some of the voltage regulation circuitry. You can see an inductor there, you know. So, all right. So we'll take a look at that under the microscope in just a second and see what lessons we can learn. Now, for the hard drive. You've always wanted to know what was inside. I know you. I know you want to know. I want to know. This is out of our old TiVo from years ago. 2005. Had a whopping, what was it, 80 gigabytes? Does it tell us here? I'm sure it does, and I'm just not seeing it. The WD-800. 5 volt, 12 volt. Lot of. Where is the capacity marked? I don't know if it's 800 or 80. There it is, 80 gigabytes. Just wasn't seeing it. So this is an 80 gigabyte hard drive. And the one that came out of that storage was 2 terabyte. Talk about a big difference. And I'm sure back then we thought 80 gigabytes was cool. Come on. There, now. I should have made these a little bigger. Put the spacing a little bit better. All right. So these things are hermetically sealed to keep dust and debris out, but it looks like all that I've got left is a hidden one that I should have remembered. But there is a hidden screw near the bearing. Whoops. It's been a little while since I've demolished a hard drive. Okay, so there's one. We got to get that guy out. Are we having fun yet? Any day I get to take something apart and learn something is a good day. Okay, there we go. All right, so here is the inside of our hard drive. We've got these platters. You've got a read-write head that moves very precisely. So the basic way that this thing's working is this will spin around at, depending on the hard drive, either 5,400 revolutions per minute or 7,200 revolutions per minute. And then as it does that, the read-write head moves over it. And the read-write head is flipping the magnetic state on the hard drive to write and reading the magnetic state to read. And there's multiple platters often stacked in these things. This particular drive, it looks like it just has one platter, but you know, that's okay. That's how the old stuff worked. So one of the nice things about taking apart these hard drives is you get these wicked strong neodymium magnets. So inside the hard drive is sealed, but outside the hard drive, you've got electronics, and they've got to connect. So there's got to be some sort of a pass-through. And this is the pass-through. this connector right here is going to connect to the board on the other side, and it goes from being a a mechanical connector to a flexible PCB with stiffeners. And it looks like it's glued into this case. I don't know if I'm going to be able to separate that without damage, so we'll leave it alone for now. Anyways, once you get the screws out, those magnets are free, but man, they are strong, so be careful. This one's just a little tiny small one, but it's a very strong neodymium magnet that can pick up all sorts of fun stuff. Here we can see the, let me center that a little more. You can see a coil of copper, and you run a current through that, and then that gives us the positioning. There's a little, I guess just an end stop. I think there might be a sensor there. It looks like there's a magnet stuck right into this little piece of plastic. Let me get you on a tighter view here, and I'll share that with you. Jeremy, you can see yourself in the reflection of the disc? Are you a giant orb of light, Jeremy? Are you? Let's see. We need this one. All right. So it looks like there's a little bitty magnet in the end plastic of this piece here. And there's a piece of metal here. So I don't know if that's triggering a switch or what, or if maybe that's just locking it in place in a, just a soft lock. Because I don't see any wires coming to or from it. So maybe it's just kind of holding it in place when it's not in use. Okay, let's see. I might have to take out the platter to remove this read-write head. Nope, there we go. All right, so here's our read-write heads. And it's just these little itty-bitty sensors that hit on either side that rub over the head. And we've got these tiny, tiny wires going to them. You can make them out just there. And then they connect right here. Might have to get that under a microscope to see if there's anything. Is that a differential pair or what? It's hard to tell on this view. Then we go from that to the coil intercepts, and then we get this flat flexible cable with all of those conductors doing different things. We'll see what we can learn. And this is the part where I said it's glued, and I don't know if we can get this apart. But this goes to the outside of the case, and then this plugs in to the PCB on the other side. So all sorts of interesting stuff. All right. Did you see yourself in the reflection of the disc? You're a camera now, Jeremy. Really? No, I'm just teasing, man. Thanks for joining us today. But you should never, ever leave one of these magnets behind. They're too powerful and too good. You can stick them on anything. Screw them into the wall. They can hold up a pair of pliers. Put them on your tools. If you screw them to a tool, you can then attach your tool to something. So never leave one of those magnets behind. And by the way, once you open up one of these devices, it's toast. If you're not in a clean room, I mean, there was contamination on this thing once I took the lid off. And it's all contamination I introduced. But if you really want to mess with them, you just run that magnet over the top of it and it's done. It shan't survive. Okay. So we're just going to continue taking stuff apart here. So oftentimes, this is an older hard drive, of course, but oftentimes you'll see multiple platters, multiple read-write heads all put together. And these things attach to a motor that can be driven at precise speeds. And that's this stepper right here. So Jeremy, how did you find me today? Was it the Discord link? Because I didn't advertise this on LinkedIn or anywhere. Okay. So there, that is free. We're just left with the circuit board. Here is the backside of our stepper motor, you know, ready for repurposing if you wanted to repurpose it with anything. I assume those are just standard metric fasteners, but might want to put one or two of those back anyway. But anyhow, there's our thing. All right. I will put those screws back in later. I don't know that I'm ever going to use that, but probably best for me to set it into a drawer and move it around for a few decades before I get rid of it. That's usually my MO. Okay. Is that free? That's free. We are disassembled. Okay. Get all this stuff out of the way. And we will move over to our microscopes and take a look at stuff. All right, so what we've got to play with are two PCBs that I have made a mess with. Chester says hi to everyone, which very well might just be Jeremy at this point. So we've got two PCBs. We've got the one out of the network hard drive, and then we've got the one out of the hard drive. So this is going to do all the data processing and create a digital signal that gets sent out to this. I mean, granted, it is a different interface, but it's the same basic process. And then this does the processing and sends it out through the RJ45. So all of that to take magnetic states from here and convert that into data that travels along your network. That's pretty crazy to think about. Can you, I mean, I don't even know what all this stuff does, but can you imagine the amount of firmware writing that had to go into this, the amount of electrical engineering that had to go into this, the PCB layout that had to go into all of this, just so that you can figure out if a little spot on this is like a north or a south pole and see it on your network. It's just fascinating. Absolutely fascinating. Okay. Our friend Chester always likes to announce his presence whenever I'm doing live video. Wrong camera. So this is the wide angle overhead view. I guess we can look at that first. Some really small parts on there. And really big ones. There's a via fence all the way around, but they only tied it down in a few spots. They only soldered in a few spots, which I find interesting. And then a bunch of little jelly beans on the backside. So that's that one. And then our hard drive from 2005. We've got big old logic board, and it's actually not that big. Some nice heavy traces. This is where we intercepted the stepper motor. So that must be our stepper motor driver and feedback circuitry. So let's take a closer look. Let's see. Hi, Chester. What are you telling the viewing audience? That you want to do a cameo? Yeah? Okay. Well, anytime you want, buddy, just come on over onto the screen and we'll make you internet famous, I promise. All right, so let's start at the motor just because that's the part that went under. So we've got just some spring clips. So this logic board can be put in without any additional people, doing any additional soldering or anything. So you can assemble this all on an SMT line and just drop it right on to the board. We've got a big fat MLCC, multi-layer ceramic capacitor for C14. It's just a big bulk reservoir cap to deliver energy whenever this thing needs it. This appears to be a diode. Let me see if I can get a little better focus for you. These things are standing pretty proud, so a couple 1Ks. We've got Smooth by ST. I like that branding. So this guy's job then is to deliver the current to the motor and keep it running at a constant speed so that the data that comes off of it is basically sent at the right baud rate. Looks like they jumped this first pin. They ran it through a via on the bottom. Usually for the high currents, the wide ones like this, I tend to use more than one via, but that's just personal preference. It would have been tight, but they certainly had room. Nothing too exciting or interesting surrounding this motor driver. They, something like this dealing with high currents has the potential to create quite a bit of noise, but they've got capacitors all over here, a bunch of resistors. It's actually a lot more complicated than I would expect to run a brushless DC motor. I don't know why that is, why there are indeed so many connections. If this is indeed all this is doing, and I don't know that it is, it could have some other data connections I'm not aware of, but I can't understand why you would need that many data lines going off of it. I could imagine a few for sensors. Maybe this does more than just run the stepper motor. I mean, we'd have to Google that. If that's doing some data processing too, I mean, that might make sense. Looks like there's a missing IC. There's a bunch of test pads over here on the bottom side. And it really does look like an unpopulated IC, but I don't know. It appears that, oh, you know what these things could be? I bet you, okay, I take all that back. It looks like if we go from here to the back side, we see test points. So those vias are connecting to test points that are used for either programming or testing that IC. So that makes a lot more sense then. So these things aren't running all over the board necessarily. They're just there for programming and testing. Okay, that I buy. I don't recognize that. Is that a Maxim logo? So now this guy, based on its size, has got to be dealing with the data. This has got to be doing with the data transfer, buffering, all that sort of stuff. So we see traces running all over the place for that. Now, fortunately, though, it looks like these things are real easy runs. So whoever created that IC had, I mean, this is purpose-built. They had this in mind. Otherwise, you tend to see a lot more vias, but you never see that many traces running parallel to one another unless the IC is designed for that. These things are all designed to work together. Otherwise, it's a nightmare routing this stuff. And they don't seem to have had much trouble at all. You can see the copper's kept back from the board edge by a decent distance. I'd estimate that 15, 20 mils. It's impossible to tell without calibrating the microscope. So I could be off by a lot and I wouldn't know. Combination of thin traces and thick traces. The wider ones, the current carrying, sometimes I do like to use multiple vias, and it looks like they did too, but they did it sporadically. I can't explain that. So all in all, a very complicated board for 2005 tech. Very small parts, smaller than I would have expected they were using in 2005, but not so small, right? We're down to 0402s, maybe a couple no, I guess just 0402s. So anyhow, interesting. I like it. I like it. All right. Now for our other board. So this is the from the Netgear Hard Drive board. So this is much newer technology, and we start getting into ridiculously small stuff. You know, 0201, 10005, 01005, there we go. Combination of HDI, you know, that just go one layer down to the next, and through-hole traces on this thing. The only way that's affordable is if you're making a ton of something. That's some ugliness right there. They didn't clean their solder. And if you leave that on over a long period of time, what it tends to do is continue to etch away at the board, and it causes problems. So whenever you see that rosin stuff, if you ever have a board that doesn't work, if you can see joints that look like that, and the board's several years old, you know, 18 months or older, or a couple years, reheat those joints and see if that doesn't make your project work again. Sometimes you get lucky. So we see a smattering of test points. You can see some patterns that we're going to look at the other side to see if those are indicative of anything. But, you know, these little 5-spot patterns. You know, we're looking at some differential pairs that are crazy small. Lots of space to surrounding nets. That's to help avoid inductive and capacitive energy transfers. I'm seeing what looks like a lot more solder flux show up on the surface. You can also see the fiberglass pattern underneath if I hit the light just right. You can see those little squares. That's the warp in the weave. Now, typically what you want to do when you're running differential pairs over any significant length is run those differential pairs at an angle to that weave. Because every now and again you get unlucky and you'll have one trace over the fiberglass and one trace over the space between the fiberglass. And that space is filled with epoxy. The I can't think of the name right now, but basically the speed of propagation is different for epoxy than it is for fiberglass. So these traces can travel at different speeds. And you tend not to want that. The way around that is that you run these things at a, you know, you don't have to go full 45. You could do 10 to 30, you know, not even that much, 10 to 20 degrees, you know, run them at an angle. And depending on the type of fiberglass you have, you can choose that angle a little more appropriately. But here's something that is interesting, and I love seeing it. So here, the differential pair had to go down to another layer. These vias are to allow the return signal to hit those other layers. Now, why those layers aren't connected to this copper pore, I couldn't possibly tell you. They must be different nets. But typically, you know, if this is, say, ground, you would have those vias connected to it. So as those signals transition to other layers, there's a return path to follow. Let's see if we can figure out what's on the other side there. A crystal? No, here. So what do those vias connect to, I wonder? Interesting, interesting. And then that via is really close. What is it doing? They have these two vias in this exclusion area, which I couldn't tell you why. I would have tended not to do that if I could help it. I'm not going to be able to figure out which one that is. Let's get back to here. So we follow the traces. We hit, I don't know what that device is. Could be a double cap. Man, these things, there is leftover solder flux all over this thing. This actually might be a failed board. I don't remember exactly why I stopped using this thing. It's been so long. But there is schmutz all over. And that schmutz eventually does destroy your board. Okay, let's keep looking, let's keep looking. And if you have anything out there that you want to see, let me know. So here's the schmutz up close and personal. This is the old school brown rosin. And flux is an acid. Its job is to clean the surfaces and provide an environmental barrier so oxygen can't get in and recontaminate a joint. But like I was saying earlier, if you ever have a board fail and you have this type of stuff, it never hurts to reflow it and just see what happens. Because sometimes it will get in there and oxidize around the part or around the pin. And if you reheat it, you basically remelt it and you give yourself another chance. It doesn't always work, but again, sometimes you get lucky. Don't be like Western Digital. Clean your boards. Okay, let's keep looking around. So you're going to see spots where they did copper pores and spots where they didn't. They left copper exclusions. It's pretty common to see copper exclusions around high-speed lines, signals like this, so that you don't transfer the noise into your reference plane. So the only thing that you do typically want to see is that you want these magnetics to be, where am I? All right, so here's our RJ45. That's what we're looking at right now. And you typically want your ESD to be right there. You don't want there to be a whole, God, look at all this yuck. Black yuck. What is it black for? Anyways, you don't want there to be much space from this to your ESD's electrostatic discharge, and you don't want hardly any space between that and your magnetics. You typically want the magnetics as physically close as you can. And I don't see any reason why they couldn't have brought these magnetics so much closer. So there's 4 wires. These are actually, they've got to be the 4 differential pair or wires. So 2 differential pairs, 2 for transmit, 2 for receive on the RJ45 connection. They go into these magnetic pulse transformers, so they provide galvanic isolation from the RJ45 in case it's accumulated some amount of DC offset. So on the other side of it, you get your differential pairs coming out again. But why is it so far away? That's a great question. I don't know. Was it that far away on purpose? Did they screw up? Was it an assembly thing? Was it a case thing? They needed it moved away because something else was around there in the case I didn't pay attention to. Looks like we've got some solder mask scratching. I don't think that was me. Interesting. So here we've got a small power rectifying circuitry. So I'm guessing that's some sort of a power management IC. Again, some missing solder mask. You can see the copper shining through clearly there. That's a no bueno. That's an inductor. Looks like a linear regulator. More flux and schmutz around here. Boy, I tell ya, Western Digital, I'm judging y'all really hard right now for putting out a dirty board. Another inductor, another what I assume is a power management IC, bunch of capacitors. What looks to be a missing IC, or maybe some jumper test points. I don't know. Let's hook up the, let's warm up the soldering iron and see what else we can get into. All right. So while I'm giving that a second to warm up, please let me know if there is anything that on any of these boards you ever want to know more about. I am more than happy to look into any part of this. Oh, I know today's kind of a weird day because I didn't advertise, because I didn't know, and I still don't know if I'm even on air right now. So what I'm using right now is flux and something called Chip Quick. This is a 4 eutectic alloy blend that I'm going to add to these joints, and it will drastically lower the melt temp. This is the pulse transformer. Let's put something under there. It stays kind of flat. So I'm going to melt this on both sides of the pulse transformer, and then I'm going to heat them both up, and I should be able to pop that pulse transformer. And then with any luck, I can see what's under there and see if there's a reason why they have that pulse transformer so far away. I don't know. This stuff melts at a very low temperature, which is fantastic, but it's also incredibly fragile. It breaks incredibly easily. So I'm just going to heat up one side, heat up the other. And off we go. Now I could, if I was going to resolder this, I could reuse it, but I'm not. All right, so this is something that's interesting, although it doesn't answer my question. So on one half of the pulse transformer, on the input side, there's a copper exclusion, but once we start getting to the output side, they put in a copper and a via stitch so that all of those signals have qualified return paths, but so that none of these do. I don't know. I feel like there's something I'm missing. So, first of all, signal return path, abso-flippin'-lutely. Um, don't have an issue there. That's great. Why don't we have one over here? And then why did we do this so far away from the connector? That's like a solid inch. I can back out to another view for you, just to let you know what I'm looking at. This is the RJ45 input. This is the magnetics. It's a full inch away. Why? That's an inch for noise to propagate. So then did they decide that the way to fix that was to cover it in that metal shield that we saw so much earlier? I mean, why not make this whole part, shift it in? Obviously they wanted the magnetics hidden in there, but I don't get it. I'll either have to do some research or live not knowing. Maybe one of you folks out there in TV land can tell me. I don't know. So, all right. So this is a magnetic pulse transformer. And inside here, this little guy, there's a bunch of little coils of copper around ferrite cores. And I don't know if you're curious like I'm curious, but we're going to very gingerly, sorry, I dropped a little chip quick there and it's rather expensive, so I want to make sure that gets put away. Rather gingerly, smack the heck out of this with a hammer and see if we can't get inside. I don't know if we can. It could be epoxy and then we're out of luck. I don't know. Looks like it's a solid epoxy case. Yeah, that's not coming open. Okay, well, sorry, but this is a pulse transformer. If you ever want to, take a look at a data sheet for those. It's kind of an interesting arrangement. I don't know who came up with it, but you know what they say, clever, clever, toilet lever. And then probably the final thing to look at before we're done here for today is let's take a look at this read-write head a little bit closer. Okay, so yeah, there was so much that wasn't visible to the naked eye. So these are the read-write heads. They are tiny little guys, tiny, tiny. I'm going to bend one back so we can look at it flat. So we've got wrapped in a really interesting way. It's actually a 4-wire connector. And I don't know if we can see what that is. We're going to try. I can make out some interference patterns that might just be optical artifacts. I can't really see. So this is the magnetic head, and I forget the physics effect that they use to read the magnetism and write it. If it's giant magnetoresistance or what, I just don't remember. But we've got 2 traces that come in on the bottom, 2 more on the top. They're routed together almost like differential pairs. I'm going to back out a little. Two of these traces are much thicker for most of the run, so I'm assuming those power the either power the sensor or they power the write cycle. You might want to put a little more energy into it for that. And then those things, God, this must have been a nightmare to assemble. Those things run down, and here the other ones fatten up too. Huh. All of this on flexible till it comes down, and till all those things connect out over here. These trace sizes are all over the map. I don't understand why. And then those run to a, is that an integrated circuit that's potted on there? There's no topside markings, so I'm never going to know what that is without an X-ray. I'm just saying, if anybody wants to buy me one, I wouldn't say no. And then we leave that IC and go into the connector. So they're using a little bit of copper just to identify the part. So, all right. Anyhow, with that was our, man, I got my little thing, my little doohickey dirty. But that was our board. That was kind of interesting. I've never looked at one of those write heads underneath such magnification before. Is this the connector for that? Is that it? Or is this it? We didn't exactly figure out where this thing connected, did we? I don't know. I'm going to live not knowing. Crazy, crazy. All right. Well, with that has been Mark Voids a Warranty for this Friday, and this will probably be the last one for a couple weeks until the new year. I really do hope that you enjoyed joining me today, and I'd like to thank our sponsors, Advanced Assembly and Royal Circuit Solutions, for making Mark Voids a Warranty happen. This is probably at least our 20th Mark Voids a Warranty. That's right. There's 19 more of these for you to enjoy, and I got to tell you, I use the sledgehammer pretty liberally in a lot of them. So if you liked this, please make sure that you like, subscribe, hit the bell if you want to be notified the next time I'm doing it. And for goodness sake, please share these with your friends, with your neighbors, with your friends' neighbors, and with your neighbors' friends. We're trying to get our subscriber count way up. And the only way that happens if there are people like you who appreciate this content, who do take the time to like and subscribe. I know it seems like a small thing, but it matters to me. So with that, thank you again. I appreciate your time, and have a wonderful holiday season. Bye.